Today I want to tell you a little trick about ice boxes. I want to talk about some assumptions that we make based on significant figures and when we are going to decide to ignore an X, which sounds like I'm maybe going to give you some dating advice, but we're going to focus on our ice boxes and how the concentration that we start with initially relates to the equilibrium constant. So let's just dive into an example, and then we'll kind of get into the whys and hows of that. So if I have 1 molar nitrogen dioxide here, and it's allowed to reach equilibrium, and here's my reaction. So I'm forming nitrogen monoxide and oxygen gas. So homogeneous equilibrium, everybody's in the same phase. What are the equilibrium concentrations of the reactants and products? So when it's asking about equilibrium concentrations, we know we're going to do an ice box. So we break out our ice box here, and our initial amount is going to be the concentration that we're given, which is 1 molar. We're not given any information about our products, so we're just going to put zeros in there, just kind of as space placeholders. And now our molar quantities are going to change with the coefficients that we have up front. So my reactants, I'm going to get smaller by 2 times whatever that quantity is, whatever that change is. I'm going to get larger by 2 times that for my nitrogen monoxide, and I'm going to go up by an X for my oxygen. Okay, now I add my initial and my change together to give me my equilibrium concentrations to finish out my ice box here. So I have 1 molar minus 2x, 2x, x. Now, when we plug this into our equilibrium constant expression, we can see here that my equilibrium constant is quite low. So this means then, if we write out what our expression is, because I always like to have it in front of me, concentration of my products raised to the coefficient power multiplied together divided by the concentration of my reactants raised to their power from the balanced chemical equation. So that small number then indicates that I have a lot more reactants in my equilibrium solution than products, right? My denominator has to be a lot larger than my numerator in order to get such a small number. So at equilibrium, this naturally sits more on the reactant side of things. So that's what that tells me there. Now, when I plug in my equilibrium concentrations, as is the next step, then I have 2x, which I'm going to square as my x, divided by 1 minus 2x, and I'm just going to drop my units for now, squared. Now this all looks kind of ugly, because then this would give me a 4x cubed on the top, and then we'd have this 1 minus 2x squared, so we'd have to kind of factor things out. We'd have to do all the things, expand out kind of this this expression. That looks kind of ugly. This would be challenging to solve because we have a bunch of powers in there that make it tricky. So I wonder if there's a trick. There's a trick. That's the good news here. So this kind of gets to what we're talking about with ignoring the X. When we're ignoring the X here, we're ignoring the X with respect to the concentration. So what we're doing here is we're comparing this initial concentration with the equilibrium constant. So I'm just going to do a little sketch out to the side here. So if I have 1 molar for my concentration, and I think about this number with respect to this number, so I'm going to expand this out. So I'm going to go against my natural tendency and put this in decimal notation as opposed to scientific notation. And when I write out this number, if I think about how these things would be related together, for example, if I'm subtracting 2 times this amount, even if I had 2 times this amount, so if this was a 0.00024 at the end, then if I was to add or subtract these together, then I would add them together, I'd subtract them together, and then I would still round to the hundredths place because of significant figures. So because of all these extra zeros here, no matter what I do, even if I multiply this by 2, even if I multiply this by 10, even if I multiply this by 100, it's still not going to have any impact on this number. It would still give me 1, right? It's still going to round. So the secret to this is if there's a large enough magnitude difference between the K value, my equilibrium constant, and the concentration that I'm comparing this X to, which is giving me information about kind of how this thing changes to reach equilibrium, which is related to this K, then I'm going to be able to just ignore it because realistically, it's not going to have much of a difference anyway. So what I'm going to do here is I'm going to disregard this X. I'm going to ignore this X. Block it on social media. And now that cleans up my math a little bit because now this is just 1 squared and this on the top is just going to be 4x cubed. So 4x cubed over 1 squared, just for clarity's sake, which would give you 4x cubed. And then now you have 4x cubed is equal to your equilibrium constant. Now that's math that you can do, right? So now I divide both sides by 4, then I end up with x cubed is equal to 3.0 times 10 to the negative 6. And now I can take the cube root of each side. And when I take the cube root, then I end up with an x that is equal to 1.44 times 10 to the negative 2. And that's the nice thing about cube roots is with squares, we have to usually factor in the positive and the negative and figure out which one is physically possible. But when you have a cube root, then the sign matters. And so if you have a positive number, it has to be a positive number that goes in. So that's kind of that's the good news there. Okay, so if that's my x, then to solve the problem that I'm given, which is what are the equilibrium concentrations of each of my reactants and products, then my reactant here, my nitrogen dioxide, is going to be that 1 molar minus 2 times this value here, which gives me 0.97 molar. My concentration of my nitrogen monoxide is going to be 2 times this, which is, of course, 2.88 times 10 to the negative 2 molar. And then my concentration of my oxygen is just going to be that amount. That was sort of what you solved for. That was X. Oxygen was your X. Okay, so when we're looking at this and we're kind of figuring out, well, do my numbers make sense? Does this jive with the overall information that we're given? We have a very small K value, right? This is a small in magnitude, so we would expect that we have a lot more of my reactants than my products. If we compare these values, we can see that that fits pretty well. So realistically, I went from 1 molar nitrogen dioxide to 0.97 molar at equilibrium. So I didn't use up a whole lot, and it was happy that way. So in general, it likes to be nitrogen dioxide. It likes to sit on that side. It's still going to break apart. I'm going to get a little bit of each of these guys, but realistically, it's going to sit more on the nitrogen dioxide side. So this would not be a very efficient way to produce oxygen, if that's what I was trying to do, or this would not be a very efficient way to produce nitrogen monoxide, if that was what I was trying to do. So that's why this information is interesting and useful, kind of from an experimental standpoint. How would we use this in a lab? Is if I'm trying to figure out kind of efficiency of processes, using those equilibrium constants and thinking about how much I can start with, kind of playing around with how much I would end up with at some sort of equilibrium setting, that's going to give me information of how to proceed. Is this enough? Is it too much? Etc. All right, so our general rule here for ignoring the X is if there's a difference is greater than 10 to the third. So that is a very loose rule. That is not a law. That is not a rule. That is, different people have different guidelines on this. But in general, in very general terms, if the difference is greater than 1,000 times, then we can ignore the X. And so if we see kind of our 1 here compared to the 10 to the minus 5 of our K value, that difference is significant enough. It's a greater than 1,000 times difference. This guy is greater than 1,000 times smaller, I guess. Greater than 1,000 times smaller. That's a weird way to say that, but I'm sticking with it. So there's a big enough difference between these two that we can ignore the X for the sig fig reason. That's why sig figs are important. Well, one of many reasons why sig figs are important. as I'm always saying. All right. If you have any questions on this, don't hesitate to reach out. Otherwise, I will talk to you again soon.